The International Space Station is a remarkable example of what it takes for human habitation in space, as everything that a human needs to survive, down to what we need to breathe, must be created within the station itself. So if any major system fails to provide what a human needs, everyone within the station will die. So similar to the moon landing, the ISS is a great starting point for the future of human space travel, as every piece of engineering that goes into its design is a response to the challenges that space will bring, and what it will take for humanity to thrive in space. So for context, the ISS started out as a joint operation between the United States and Russia, with the Russians building the Zara module, which was launched into space on November 20th, 1998, and the US building the Unity module, which was launched into space a month later. These two modules were then connected 2 days later on December 6th. For the next 2 years, the ISS was remotely tested and monitored from the ground, with NASA and Roscosmos testing the station's power, propulsion, and communication systems. And once it was all safe and ready, the Russians constructed and launched the Zvezda module on July 12, 2000, which finally docked several days later on July 26. This third module was crucial, as this is what made the ISS habitable in the first place, and it made it an official space station. It brought the important oxygen generation systems, sleeping quarters, water storage, and a few small solar panels, which would later be improved with other modules. And by October 31st, 2000, the long-term mission named Expedition 1 was put into motion, with the launch of the Soyuz U and the first ever long-duration crewed mission aboard the ISS, consisting of 3 astronauts, 1 from the US and 2 from Russia. The crew was transported onto the ISS from the Soyuz TM-31 spacecraft and would remain on board for the next 5 months, receiving supplies, installation of large solar panels, and a new laboratory module, before eventually departing on March 19th, 2001. Expedition 1 was just the start of the ISS missions, and the term is sequential, in that every new crew rotation on the ISS, the mission name would increase by 1, with the most recent mission, for example, being Expedition 70, being active as of 2024. Ever since the first crew on board on Expedition 1, there's always been a human presence on board the ISS. Every 4 to 6 months, new crew members are brought on board the station, where they meet the current crew, and afterwards, that crew, the previous crew, then also leaves the station using the same spacecraft they used to get on board originally. And speaking of which, there's always at least 2 spacecraft docked on the station, and these spacecraft are used to both get on the ISS from Earth and leave the ISS and return to Earth. And that leaves us to where we are now, with the ISS being the single most expensive piece of technology ever built, with an estimated $150 billion cost over its entire lifetime, funded by the US, Russia, Japan, Europe, and Canada. I mean, just for reference, a single aircraft carrier is around $10 billion. And this station orbits around 250 miles above us, or 400 kilometers in superior metric units. The International Space Station is essentially comprised of several modules connected together, sort of like a bunch of Legos stuck together. And again, this is because there was just no way any rockets were going to be able to send a structure of that size into space on only one rocket. Earth's gravity and atmosphere is just simply too much for that. So each piece was sent up individually. And speaking of which, for any type of space mission, especially in regards to space missions involving traveling to the ISS, it starts with rockets. A single rocket has a height of 200 to 400 feet, or around 100 meters, and usually weighs a couple million pounds or kilograms. Rockets use propellants to reach their escape velocities. Propellants are chemicals that produce thrust when burned, whether it's liquid or solid. The propellant is made up with a fuel and an oxidizer. The fuel provides energy, and the oxidizer provides oxygen, which is needed as there is no air in space. These two are ignited with a kind of spark plug, which ignites this mixture of fuel and oxidizer and creates thrust. This thrust is the rapid expansion of hot gases, essentially a controlled explosion. The fuel and oxidizer are highly reactive substances, and when mixed and ignited, chemical bonds break, and this energy is released in the form of heat and light. These gases are at a high temperature and therefore have a higher energy in the form of kinetic energy. And hot gases also have less density, which makes higher pressures. This high pressure causes the molecules within the gas to vibrate intensely and move extremely quick, causing this gas to be pushed out of the nozzle and create this immense thrust. In a rocket launch, there are in general 3 stages. First stage is the liftoff. This stage lasts around 2 to 3 minutes, with the main engines firing, producing millions of pounds of thrust, accelerating to thousands of miles and kilometers within a few minutes. And within these few minutes, the rocket reaches around 50 miles or 80 kilometers up in the atmosphere. With that, the first stage main boosters separate and fall back to Earth to be reused for later works. So after this first stage separation, the second stage boosters ignite, and at this point the rocket is officially across the Kármán line at around 62 miles or 100 kilometers above the Earth, officially entering space. At this point, the rocket continues to accelerate until it reaches a speed of around 17,000 miles per hour, or around 28,000 kilometers per hour, which is known as orbital velocity. Well, at least the minimum requirement for our planet, where Earth's gravity pulls on an object, but since it's moving so fast sideways, the Earth just curves away beneath the object, creating a stable orbit, which is essentially what the ISS also does. It's also in orbit, perpetually falling towards the Earth, but always missing it. That's kind of just how things stay in orbit, basically. So once the rocket reaches this orbital requirement, the second stage boosters shut down, and the rocket officially separates from the crew. And the spacecraft is all that's left. The third stage begins, and now it's all up to the crew to perform small thruster adjustments to match the ISS relative velocity and height, and finally finish docking, where they meet the other crew, hug, shake hands, and act like the big nerds they are. As a low Earth orbit space habitat, it must be able to withstand the harsh conditions of celestial objects, just like any space structure, which includes protecting itself from micrometeoroids, debris, and even radiation. So when it comes to the station's structure, it's mainly just made up of many different layers of material, mostly aluminum. For example, the first layer is often just using aluminum alloys with other strong materials. That first layer, the outer shield, is just there for impact dispersion. And again, this is possible because materials like aluminum are not only strong enough, but also flexible enough. They're able to bend and flex without breaking or causing too much strain. And just below that are the further intermediate layers, stuff like Kevlar and Nextel, all those other stronger ones that just simply absorb more of that energy. And then finally below that is just the pressure hole, which is the inner layer with, the airtight seal. This is what keeps the air in and keeps the astronauts safe. And this multi-layered hole is necessary just to stop what are sometimes just really small micrometeoroids. Micrometeoroids are small, dust-sized rocks of material that are capable of piercing through space objects. And despite being so small, these are dangerous in space due to just their sheer velocity. As in space, there is no air resistance. And they move so fast that instead of just vaporizing on impact, their speed allows them to pierce through these materials. So that's why strong, flexible, energy dispersing materials like the one you see on the hole are necessary for these type of structures. But even then, something as small as like a brick-sized object can be a threat that the ISS has to avoid. So the hole is mainly there to protect against micrometeoroids, but when something bigger, and when I mean bigger, something as small as like, football or something, when something like that approaches, and the ISS has to move and make thruster adjustments just to stay away from dangerous celestial bodies like that. Moving on into the interior of the space station, there are many systems on board designed to keep the humans living there alive. For example, oxygen production. On the ISS, there are 2 primary systems responsible for oxygen production. The Electron system from the Russian segment of the station, and the oxygen generation system from the US segment. Both act as a backup in case either one fails, and both use the process of electrolysis to reduce oxygen. Electrolysis is the process of splitting water, H2O, into hydrogen and oxygen, using electricity. The system uses purified water, either acquired from Earth or even from the crew from sources like their own urine. So in this process, this electricity is basically just free electrons, going through a current that must have enough voltage so that once the electricity enters the container where the water is contained, it can then weaken and break the molecular bonds within the H2O, separating it into gases. And this is done through the use of two different metals placed within the water and the container. One acting as a negative electrode, the cathode, and the other one acting as a positive electrode, the anode. Electrodes are basically just conductive materials that allow an electric current to enter or leave a system. And this electric current, the free electrons, aka electricity, comes from a power source like a battery. So when this electrical current flows from a battery into the negative cathode, it causes the water to lose electrons, creating oxygen gas. This whole process basically creates what we call an electric circuit, and is also how some electrical devices like chargers function. This is electrolysis, and typically that is all that is needed to create oxygen in an electrolyser. However, due to the ISS being in, space, gravity affects this process a little bit more differently. When electrolysis happens here on Earth, the oxygen and the hydrogen gases simply just escape and float away from the water. Since, gas is lighter than liquids, obviously, it just floats up. But in space, gas and liquid don't weigh anything. So the gas just simply gets trapped in these bubbles and simply just sticks to the water instead of being separated. So to fix this, the electrolyser is designed with a spinning mechanism that essentially centrifuges the water, which can separate the gas bubbles from the water. And since while in space they may not have any weight, they have different densities and masses, which can be separated by the centripetal force of the machine. And then from there, the machine can simply just suck up this oxygen, put it into another container, and there you go. You got clean, fresh oxygen. And with this, the ISS can generate enough oxygen for all of its crew members, and only really needs a resupply of oxygen and water every few months, just in case. And speaking of water, as mentioned prior, the ISS has periodic resupply missions for oxygen and water, but water can still be produced on board, similar to the way oxygen is produced on board. Especially in one way that's pretty odd, but still strangely impressive. Astronauts, through recycling their own urine and body sweat, can reclaim and reuse almost all the water on board, around 90%. As NASA's motto says, yesterday's coffee is tomorrow's coffee. Astronauts use a machine called the urine processor assembly, where the urine is funneled into the unit where it undergoes a vacuum distillation process to evaporate water from urine. Again, thanks to zero gravity, this machine is designed slightly differently to use centrifuges similar to the oxygen generators on the ISS. In this case, though, it separates waste from water instead of, gases from liquids. So in this machine, the urine is spun around and centrifuged and heated to the point of boiling, where then water vapor is created. And again, since water vapor is just, water in a gaseous form, it's lighter than the liquid urine spinning around, so it can then just be separated and moved into another chamber. From here, the water vapor goes through many different filters to remove any other volatile organic compounds and contaminants, and eventually it is cooled down so that the water vapor condenses back into liquid water, where it's purified furthermore with other methods like iodine and microfiltration filters that physically remove, any particles and bacteria from the water. And once that's all done, finally, you're left with clean, purified drinking water that is probably the most filtered water compared to anywhere else on Earth. And when it comes to the food on board the station, compared to the other life-sustaining resources like water and oxygen, food is unfortunately one of those main elements of the ISS that it just can't really reproduce or reuse in some way. Most of the food on board is designed to last for at least a year or two, and that's based on the astronauts' diet, that being 3 meals a day, similar to here on Earth. Obviously, the food can probably last longer if it was rationed, but that's not the main point. The main point is that no matter what, food will run out. So the crew on board instead just eats when they need to. There's no ration or anything. They eat a varied diet of different foods. But yes, a lot of the food on board is great at lasting a long time, some of which include tortillas. Yes, I know, amazing. Tortillas are actually preferred over bread because tortillas don't produce crumbs. Along with this, the ISS also stores protein powder, canned meat, dried fruits and vegetables that can then later be rehydrated, and nuts for that fiber. And kind of niche, but still very important for humanity's long-term goal for space travel, honey. In fact, honey, like many other foods I just mentioned, is really important for this type of space business. Honey never spoils. It literally lasts thousands of years, is nutrient dense, packed with sugars, and even has medicinal effects due to its antimicrobial properties. It's up there with all the long-term foods, man, right next to hardtack crackers, pemmican, and rice in terms of its benefits. Now, just to clarify, just because, the ISS can't produce any of its own food doesn't mean that, growing food in space is impossible. The ISS has done experiments with growing plants on board, specifically experiments with lettuce, tomatoes, wheat, and radishes. However, full farming systems have not been implemented due to just several factors, mainly due to the ISS limited design. Remember, the ISS's main purpose is just to serve as a microgravity research station, conducting scientific research on how zero gravity affects certain things, and if it's even possible for humans to live, which we already know, yes, it is possible, for the most part. So growing food in space is absolutely possible. It's just different depending if there is gravity or not, because the ISS experiences zero gravity because there's no type of machine or whatever to generate some type of artificial gravity. But if we did build some type of rotating space station, we could generate our own little artificial gravity, which could help humans live more comfortably in space. But either way, no matter what, growing food in space with or without gravity is still possible. For example, in space, hydroponics is the most useful, as it allows for plants to grow just by using water, no soil whatsoever. Water and liquids in general just act weird in space. Liquids simply just clump together in these little bubbles rather than dispersing out like it does on Earth, which makes it hard for water to flow into the soil and into the roots, which, is what is needed for plants to grow. So instead, we just use hydroponics, which uses nutrient-rich water that can easily deliver the nutrients and oxygen needed into the roots. And add on some artificial lighting for photosynthesis, plants can manage and thrive in zero gravity. And that's all hydroponics is. It's just growing plants and foods with just water, no soil or anything. So really, that's the only real weakness the ISS has. For the most part, it can make its own water and oxygen and even its own power using the solar panels, but it just can't produce food. The ISS is just mainly a laboratory and a living space. So of course, they also have their own spaces designed for human occupation. Like for example, the cabins, which are essentially small private little crew cabins, around the size of a phone booth, where astronauts can relax and sleep by strapping themselves into these sleeping bags so that they won't float around in their sleep. And along with this, astronauts have a module where all their exercise equipment and machines are located, like a treadmill, weightlifting machine, and a stationary cycle. All astronauts must work out for at least 2 hours a day. And it's one of the main reasons why astronauts are such big nerds and such fit bastards at the same time. It takes a lot of brain power and muscle power to be one. And along with this, it also takes a lot of willpower as well, because there's two things that become quite difficult in space, and that's urination and defecation. Like I said before, luckily you can just pee, into a little tube and then you just filter that, and there you go, you have your drinking water. But defecating is also a big problem. But luckily, again, engineers have come up with several ways to alleviate these problems for both men and women. As I just said before, with peeing, they just use a hose with a funnel attached, where then the urine is just collected and then later processed and purified into the drinking water. And as for taking a shit, they thankfully don't have to shove some type of vacuum hose into their asshole or something. Instead, they just simply use a toilet with a small fan-powered vacuum that pulls away any waste into a sealed bag, which is then later disposed of when a resupply vehicle visits the ISS, which comes around every few months, like it usually does. Where it resupplies the crew, and then it leaves and burns up in the atmosphere, along with the waste it carried, which is something that's actually done quite often. It's basically, there's some resupply, crafts that come up that are basically just a one-time use spacecraft. They're designed to show up and then burn in the atmosphere. And then finally, for cleaning themselves, unfortunately, they cannot shower like how we do here. So instead, they use wet wipes and rinseless body wash and shampoo, which basically means they just apply like a liquid soap with a washcloth, and then they just, rinse themselves. So everything's very physical on board because, again, liquids just behave weird in space. And lastly, for living conditions on board the station, the crew can enjoy themselves with the cupola module with its big windows where astronauts can look out and enjoy the views of Earth from space, watching the ISS complete one full orbit around the Earth every 90 minutes. And with this, I hope I was able to explain and describe how the ISS works and functions on its own, and also how it serves as a great stepping stone and training ground for future space travel and long-term habitation. It took a lot of brain power and crack to get where we are now, but thanks to these pioneers, a lot of work has been made a lot easier for us, for all mankind.